Okay. Okay, resuming, we now have these 6 conditions on the board. What do these first 3 conditions do?
They can tell you whether a number is bigger than A or not.
Good. So these, ZA is 1 if A is greater than equal to 0, 0 if A is less than 0. And what do these do?
Same thing for B.
Same thing for B. So ZB is 1 if B is greater than equal to 0, 0 if B is less than 0. And so now, let's add one more constraint. Yes?
Is there an A in the second equation?
Oh, thank you. In my notes, I'm putting in the subscripts to remind myself that it's the bound for A. Because I don't actually have to use the same bound every single time. So for instance, that's a good point. If I know something additional about A, about how big A can be, and I know something about how big B can be, I don't have to use the same value there. And that might actually help things a little bit. So what is this condition going to give us? ZA plus ZB equals 1.
AB is negative or something. There's only one positive and
I'm sorry?
for each A and each B, if you just select a pair, at least just one negative number and the other number is non-negative number.
Did you use the word at least?
No, just
Good,
exactly.
good, exactly. So, exactly 1 of AB is non-negative. And the reason is, each of these is 0 or 1. If they're both 0, they're both 1, this isn't satisfied. So if we want to choose between 2 options, I either want A to be non-negative or B to be non-negative. These constraints will force that to happen. And so this allows you to put in the beginning of an OR. So basically we want A or B is positive, but not both. And so now we can begin to put in constraints like this as well. And so, again, a statement like this should look highly nonlinear. A or B. And we're showing how we can incorporate it. Now, what's the cost? Well, the cost is we have to introduce 2 new variables and 7 equations. Okay? Now, the 2 variables are just binary, they're 0 or 1. Unfortunately, integer programming is a lot harder than just generic, real programming. And so there's a huge cost as soon as we convert to an integer programming problem. So sadly, most of the integer programming problems, we don't have fast, efficient algorithms to solve. We can get close to solutions. And one of the big examples, one of the famous ones is the traveling salesman problem. How do you visit all the cities efficiently, trying to minimize total travel time? This is an extremely hard problem. There's the bus route problem. How do you determine how many buses a school district should have, and what should the bus stops be to get all the kids to school? It seems quite clear that there is an optimal schedule. If you have 150 kids, how many buses should you have? What can you tell me about the number of buses?
At least 1.
At least 1, good. What else can you tell me? Have to have at least 1 bus. What's an upper bound on the number of buses if I have 150 kids in my school district? 150, right? We will not have more than 150 buses. So we know that there's some number between 1 and 150. So for each number k, if we have k buses, we look at all the ways to break the number of 150 kids into k groups. Then for each of these groups, we look at all the ways to order the stops. There are only finitely many possibilities. But if you try to just brute force this, the universe will expire numerous times over before you make any real progress. So we try to solve this with linear programming. Unfortunately, we don't necessarily have great integer linear programming algorithms to solve these issues. And so unfortunately, we can't just immediately write down the optimal solution. But for a lot of these problems, while it would be nice to have the optimal solution, if you're close to the optimal solution, this is good enough. Right? And so even if we can't find the optimal bus route, if we're within a few minutes, then that's not so bad. Now there may be a bunch of constraints we want to put into the bus routes. You know, one constraint might be the maximum amount of time any kid has to spend on the bus, which in some sense is equivalent to when the bus leaves and when the bus arrives at school. And so you can easily incorporate constraints like this and the method will go through. And so I'm not going to go through all the other different things you can do in integer programming. You know, some of the other things is you can actually do maximum and minimum using just, you know, the ORs and all this stuff. And so all of these things which initially look nonlinear, you can have a far more complicated objective function. Now the difficulty, of course, is always how many terms do you have in the objective function. The more terms you have in the objective function, the greater the cost it's going to be to introduce stuff like this. But you know, again, it's converting it to something you know how to do. And there's advantages to that. And as we said with the dual problem, we can often get some estimates as to how close we are to the optimal solution. So even if we're not able to solve it, if we can say we're within a certain amount, we're often pretty happy. The other thing, and this is where statistics and inferential statistics really comes into play. There's a big difference between the school bus problem and the movie problem or the airline problem. So in one situation, I'm trying to find what's the best route for the buses to take and how many buses. In another, I'm trying to figure out how many planes to buy and what route for the planes to fly. There's a fundamental difference between these two problems, and the idea what that difference is. It comes down to a planning perspective. What information do you know if you're trying to design the bus route? Where the kids live, right? People are not going to choose to move into your school district in the middle of the year based on your bus route assignments, right? You know, these are the kids I have to get to school. For the airlines, what information do they not know?
Where do people live?
Well, it's not so much where they live. Where they want to fly to and when, right? The airlines have to, and same thing with the movies. They have to try to estimate what these numbers are going to be. So, this safety in numbers, right? You know, how many of you have ever watched Seinfeld? Have you ever seen the episode where Newman and Kramer decide to recycle bottles because Michigan gives 10 cents and all the other states only give 5? It's one of the greatest episodes, the bottle deposit, 7th season, I think episodes 21, 22, 22, 23, something like that. Michigan gives 10 cents per bottle. And so they decide to take all the bottles there. But the problem is it's very expensive to drive from New York to Michigan. And so all the extra money they'll make in returning bottles for 10 cents rather than 5 cents, they're going to lose in gas costs. And then Newman figures out how to make it work. Because one day of the year is such a great day for meal delivery. What is the great day for meal delivery? Yes, what is a big
Christmas Day?
Christmas Day is big, but according to the Seinfeld episode, there is one day bigger than Christmas. There's a day bigger than Christmas. Bigger than, oh, who sends Thanksgiving?
Tax return day.
Well, that's a good one. Although, there is that is good. There's a huge spike around April 15th, but there is a day that's very big.
Valentine's Day?
They said that this one is even bigger than Valentine's Day.
April 1st?
No? Mother's Day. I'm not the right person to ask because I don't believe in Hallmark, but they say that Mother's Day is extremely big for the post office, for sending all these cards. And they have a slight overfill, and they have one truck with just a few boxes that has to go to the Michigan Center. And they can use the rest of the space to transport the bottles and recycle them and make the money. The industries do have some idea of what demand is going to be. the better model the industry has for these demands, the more profitable they can be. And so this is where you do a lot of data mining, a lot of statistical inference to try to figure out who is going to want to fly between various places. And so you start to ask yourself, which days are similar? Maybe all Saturdays in April are the same. Do you think all Saturdays in December are the same? Or could part of December be different from other parts of December? Right? You know, stuff around Christmas and New Year's is probably going to have very different flight patterns. When you have movies, maybe a movie that comes out that's an action movie will behave similar to other action movies in terms of what the initial demand is and how the demand decays. And they try to make models based on, does the movie have big stars in it? Is it a sequel? Is it an action movie? What time of the year is it coming out? What kind of advertising and promotion is being done? Does it have a hit song that's playing on the airwaves as well? And so you take all this into account and you use this to get the coefficients for your linear programming models. And that's where things get very difficult. Because to solve these linear programming problems, we need to know what to solve, right? We need the linear programming problem. We need the constraints. Well, the constraints will depend on these unknown parameters. We need to know how many people want to fly between these cities. We need to know how many people want to watch this movie at a given time of day. And so to really do the subject well and to really be useful, you have to be able to understand not just the mathematics, but the statistics used to get the numbers for the mathematics. And so that's one of the big things I want you to get out of today's lecture. As wonderful as all of this is, it would be useless if we didn't have a good way to do something to get these numbers that we need. The other thing you want to then do is you want to get some kind of sensitivity analysis. How much does your behavior change depending on the values of these numbers? So you want to try to figure out which numbers are the most important ones to understand. So when you're trying to figure out how successful a movie is going to be, there's lots of different categories you could look at. You have a certain amount of research dollars to spend. What is the best way to spend it? Which things do you want to really know well, and which things does it not really matter too much? So for instance, when you're trying to figure out what class sizes are going to be at Mount Holyoke next year, does it matter more which class is being offered or who the professor is who's teaching it? Will certain professors always generate large classes, or will certain topics always generate large classes? How do you try to allocate rooms based on who you think is going to be teaching and what size they're going to get? Accidentally, Brown once gave me a room of 12 for a class of 60. It's a little small snafu, and I had to teach on basically a little chalkboard that was used for meals, for one day until we could get a better room. There was a computer glitch. And so, these are real issues, and you want to try to figure out which numbers do you want to devote your research dollars to trying to really understand. Because you have a finite amount of resources. And so you really want to do the sensitivity analysis. So I think this is a good place to start for today. And it gives a nice